Welcome everyone. My name is András Szeberényi and I'm a college professor at Budapest Metropolitan University, and I'm also serving as the head of the marketing department. I have spent more than 15 years researching sustainability, and in recent years, my work has increasingly focused on the intersection of artificial intelligence, energy consumption, and sustainability. This topic is no longer just a technological issue. It carries significant economic, environmental, and social implications. As the title of this presentation suggests, we are looking at a dual process. On one hand, artificial intelligence is expanding at an incredible pace and appearing in more and more sectors. On the other hand, this rapid development comes with a massive energy demand. In other words, AI can simultaneously be part of the problem and a key part of the solution. In this session, I want to show you why energy has become a critical prerequisite for AI, how AI drives up energy consumption, and how it can still improve overall energy efficiency. We will cover data centers, content generation, grid management, industrial applications, and the strategic directions that appear realistic for the near future. As a starting point, it is important to clarify that in recent years, we have primarily discussed artificial intelligence as a fast, smart, and impressive technology. A recurring theme is the energy waste associated with the iterative processes of text, image, and video generation. While this often induces guilt in environmentally conscious users, we still do not pay enough attention to the precise analysis of the energy side. The digital world does not just exist on its own. Whether we are generating content, analyzing complex datasets, or managing automated workflows, every digital action is underpinned by a massive physical foundation. This operational backbone consists of high-density data centers, specialized cooling solutions, and a global network of servers and storage units, all of which require a constant, uninterrupted power supply to function. For example, in one of my studies, I found that the relationship between AI and energy is fundamentally a paradox. AI can reduce waste, assist in real-time regulation, support the integration of renewable energy, and improve grid operations. However, AI itself requires more and more energy, especially when we talk about large language models, mass data processing, or generative systems. Therefore, the question today is no longer whether we should use AI, but rather under what conditions we can use it so that it truly improves energy efficiency instead of simply adding a new load to the system. One of the greatest challenges is the projected growth in data center energy demand. According to the estimates on the slide, under an aggressive AI adoption level, energy demand could exceed 1,260 terawatt-hours. With the planned adoption level, it could be around 945 terawatt-hours, while a lower adoption might result in 670 terawatt-hours. Even with optimized efficiency, we are looking at a consumption of approximately 800 terawatt-hours. The report, which was published in the year of 2024 in the special issue of the World Energy Outlook, highlights that these are extremely high figures even in the more favorable scenarios. To put this in perspective, the planned adoption level could already exceed Japan's total annual electricity consumption for 2024. This is critical because we often tend to view AI merely as software, but in reality, every intelligent system is operated by a massive, energy-hungry physical infrastructure. My research consistently emphasizes that as AI systems become more mainstream, their energy demand grows, which could easily offset the environmental benefits we achieve with them in other areas. If we look at the global map, it is clear that energy demand is not distributed evenly. Instead, it is highly concentrated in specific regions and hubs. For instance, in Ireland, data centers now account for approximately 20% of the total metered electricity supply. In Virginia, USA, 25% of local power flows directly into data center operations. According to the global energy consumption data in 2024, the United States holds a 45% share of AI-related energy consumption, followed by China at 25%, Europe at 19%, and other regions combined at 18%. This concentration is problematic for multiple reasons. First, it places an immense load on the local power grids. Second, it reinforces regional inequalities and demonstrates that AI development is not some abstract process floating in the cloud. It relies on highly localized physical infrastructure. Research on energy consciousness in Hungary reveals that societal awareness regarding energy use remains insufficient. Many people only begin to prioritize energy issues when faced with a direct crisis, price hikes, or general uncertainty. This is precisely why we must address AI energy demand not just as an engineering challenge, but as a critical social, economic, and strategic priority. It is worth looking more closely at data center operations. This table summarizes the key differences between traditional cloud services, the AI training process, and the daily application of AI systems, known as inference. Traditional cloud computing is using primarily CPU resources, meaning it is designed for general-purpose computing tasks. In contrast, AI training is fundamentally GPU-intensive task because it requires massively parallel computations. Finally, AI inference requires a mixed architecture where GPUs, TPUs, which are the tensor processing units, optimized for multidimensional data arrays, and CPUs work together. The differences are also clear when we look at latency tolerance. Traditional cloud services require low latency because the service must be physically close to the user. AI training, however, has a much higher tolerance, as it is typically an offline batch process that does not require an immediate response. For AI inference, the required speed depends entirely on the specific user experience being delivered. From an energy intensity perspective, perhaps the most important takeaway from this table, traditional cloud energy demand is more moderate and evenly distributed. AI training, on the other hand, is an extremely energy-intensive process. AI inference is variable and scalable. Its power consumption depends on the task, the frequency of use, and the scale of the operation. Geographic flexibility varies as well. Traditional cloud infrastructure is usually located near densely populated areas to ensure fast service. AI training facilities can be built far from cities, in locations where energy is cheaper or more available. Meanwhile, AI inference is moving toward a more decentralized model, shifting closer to the network's edge, often referred to as edge computing. Ultimately, this shows that not all AI processes impact the grid in the same way. We must analyze energy efficiency separately for training and for actual deployment. As I briefly mentioned at the beginning of the presentation, we can now see the specific figures regarding the energy requirements of various AI operations. It is immediately clear that there are significant differences between these categories. Text generation consumes between 0.3 and 4 watt-hours. Image generation ranges from 1.3 to 12 watt-hours. Website generation, one of the defining trends of 2026, requires roughly 20 to 50 watt-hours. However, generating a single 5210-second video already exceeds 100 watt-hours, and depending on output settings, it can reach as high as 500 watt-hours. One area we rarely discuss is the audio generation, which interestingly is the most energy efficient. Typically, generating 2 to 3 minutes of audio requires only 0.01 to 3 watt-hours. In recent years, we have seen a constant stream of AI-powered trends on TikTok and Reels. In these moments, it is worth remembering that each short video consumes as much electricity as charging a standard 5000 mAh smartphone battery 20 times from 0 to 100%. Let's put ourselves in the user's shoes for a moment. When we say, I only made a couple of short videos, or I just generated a few images, it doesn't seem like a big deal. For an individual user, it might not be. The problem arises from mass adoption. When millions or tens of millions of people perform these kind of operations daily, it translates into a massive energy demand. This leads us to a crucial question. What can be done to curb AI's hunger for energy? This slide highlights three primary domains: hardware innovation, software optimization, and infrastructure and procurement. On the hardware side, solutions include liquid cooling systems and dedicated AI accelerators, such as MPUs and the previously mentioned TPUs. In terms of software, we utilize batching processing requests in groups for efficiency and a mixture of experts architecture, which activates only the necessary parts of a model for a given task. On the infrastructure level, the focus is on hourly energy matching and the direct use of carbon-free energy sources. This is vital because discussing it on a theoretical level is no longer enough. We know that we need more sustainable and greener AI, which requires concrete technical and organizational decisions. During my research, I conducted several interviews that revealed a significant divide in how companies view AI energy consumption as a strategic priority. Some experts believe energy is still a secondary concern in corporate thinking, while others are already striving to power their AI systems with renewable energy. This often depends on where a company stands in its AI adoption journey. There is no doubt that the technology is already here, and it is evolving exponentially. The real question is how consciously we will integrate it into our lives, our companies, and our own processes. The emergence of edge computing as a major trend is a fascinating direction. We are seeing a partial pushback against cloud dominance in favor of on-device AI. However, I must also highlight the hidden costs involved, specifically the fact that hardware becomes obsolete at an accelerated rate. This rapid replacement cycle presents a significant sustainability challenge. Consider the current volatility in hardware markets. Prices for SSDs, RAM, and other peripherals have tripled or even quadrupled within a single year. Returning to Edge AI, the core idea is simple. Instead of routing every calculation through a central data center, certain operations happen locally, closer to the source. This reduces data traffic, speeds up response times, and, in many cases, lowers energy consumption. Yet, we should not oversimplify the situation. Edge AI is not a universal solution for every scenario. Rather, certain tasks are better suited for decentralized models, while high-capacity central infrastructure remains more efficient for others. This brings us to a key takeaway. Energy efficiency is not merely a technological question, but a collection of situational decisions. Consumer habits, available infrastructure, financial constraints, and digital maturity all influence which solution will actually be viable in the end. We have reached an important part in the presentation where a different perspective emerges. While it is true that AI consumes vast amounts of energy, it is also likely that AI is currently the only tool fast and intelligent enough to effectively manage the complex energy grids of the future. Many view AI solely as a source of strain that overloads power grids. In reality, it will be one of the most critical instruments for future grid management. Why is this the case? Because modern energy systems are no longer simple, one-way models. We are seeing a convergence of renewable energy sources, weather-dependent generation, distributed energy units, fluctuating demand, charging peaks, industrial loads, smart homes, and local storage solutions. This is just the beginning. These systems will become far more complex over the next decade. Coordinating such a landscape at human speed is virtually impossible. AI, however, can monitor consumption in real time, forecast fluctuations, recognize patterns, and help minimize energy waste. In an international study that we published in 2025, we highlighted that smart grids, predictive analytics, and automated energy management systems have become dominant for these reasons. These are not merely solutions for convenience, they are increasingly vital tools for achieving true energy efficiency. The topic of operations is closely linked to grid control. I have highlighted several examples here, ranging from dynamic line rating and identifying hidden capacities to predictive weather and fault detection, predictive maintenance, and IoT-based industrial engineering systems. These applications extend even to supply chain security, oil, gas, and methane leak detection, as well as the exploration of critical minerals. Several of these elements are particularly vital because they offer more than just energy savings, they are tools for risk mitigation. If a system can forecast a failure, we can prevent downtime, minimize losses, and, in many cases, avoid unnecessary energy consumption. When an intelligent grid manages load more effectively, waste is reduced. Similarly, if an industrial system detects a deviation early, intervention becomes more cost-effective and efficient. Protecting power plants serves as a clear example. While the primary focus there is security, the underlying principle is the same. AI-based systems can analyze sensor and camera data in real time, significantly reducing false alarms and ensuring faster response times. This enhances the overall reliability of the infrastructure. From an energy perspective, this is essential, as security, consistency, and efficiency are deeply interconnected. I believe this presentation highlights a powerful duality in discussions of AI energy efficiency. Energy fuels AI, and AI in turn optimizes energy. This is a recurring synergy. On one hand, we face the reality of massive computational needs, the construction of larger data centers, and the development of systems requiring increasingly efficient server cooling. On the other hand, we build this infrastructure to enable more advanced, dynamic grids, more precise maintenance, and the discovery of new materials and methods for the greater good, such as breakthroughs in pharmaceuticals and medical devices. Therefore, the question is not whether AI is inherently sustainable or unsustainable. The answer depends on how we generate the energy, the infrastructure we run it on, how intelligently we apply it, and the level of efficiency it returns to the system. Technological progress must be paired with awareness. Recent research among the Hungarian population shows that while a significant majority is now open to energy-efficient solutions, financial barriers, a lack of information, and technological uncertainty remain major obstacles. This is where AI can truly assist, by providing personalized recommendations, real-time feedback, and accessible decision support. The insights shared today can be distilled into 3 core strategic guidelines. The first is smart integration and site selection. This means strategically locating new data centers near renewable energy sources and placing a high priority on modernizing cooling systems and overall capacity. The second pillar is incentivizing operational flexibility. We must create a regulatory and operational environment where data centers act not just as massive consumers, but as essential assets that support the stability of the power grid. The third is collaboration and skill development. Over the past decade, we have seen a continuous decline in the number of energy professionals. We must address this by introducing stronger incentives and focused training programs. While we often hear on social media that AI will eliminate jobs, it is also creating entirely new roles, making the retraining of our workforce indispensable. Ultimately, the future of energy efficiency does not depend solely on machines or algorithms. It requires a synergy of institutional decisions, regulatory frameworks, specialized training, social acceptance, and economic incentives. The future is not about stopping AI, it is about its conscious integration. We need systems that are not only intelligent, but also energy efficient. We need infrastructure that relies on renewable energy and a societal environment where consumers, companies, and institutions alike understand that energy efficiency is no longer an optional feature. It is a prerequisite. In the age of artificial intelligence, energy efficiency is no longer an issue that can be trivialized. It is simultaneously a technological, economic, environmental, and social matter. AI truly has the potential to make our energy system smarter and more efficient, but only if we remain mindful of the fact that AI itself is an energy-intensive technology. Our responsibility is to find the right balance. Thank you very much for your attention.